topic today is polar coordinates. We're going to provide an overview of polar coordinates. We'll take a look at some of the topics from the section in the text on polar coordinates, but we're not going to cover polar coordinates in a lot of depth. We'll hit some of the highlights, do a few examples, and that'll do it. First off, polar coordinates is an alternative way of locating points in two dimensions. It provides an alternate coordinate system to the typical XY coordinates that we usually use. So here's what they look like. We have a point here with coordinates x and y. That means we would go over x and up y to locate that point in the plane. But that's not the only way we could specify the same location. We could give the distance of the point from the origin and call that r for radius, and we could give the angle theta that our ray makes with the positive x-axis. So instead of defining the location of our point as xy, we could define it as r theta. The way we convert from polar to rectangular is by using the equations x equals r cosine theta and y equals r sine theta. To see where the equations come from, let's get our point back. And we note that we have a right triangle here, which means we can use the trig functions sine and cosine to relate x, y, r, and theta. In particular, the cosine of the angle theta is the adjacent side, which would be x, over the hypotenuse, which would be r. If we solve for x, we see that x is equal to r cosine theta. Similarly, the sine of theta would be the opposite side, y, over the hypotenuse. Here's my y. And solving for y gives y equal to r sine theta. So we have the two equations, x equals r cosine theta and y equals r sine theta. Those would allow us to take polar coordinates and turn them into rectangular or Cartesian coordinates. So let's say we had the point r theta, and that was the point 2 pi over 6. We're told the angle is pi over 6. That's 30 degrees, so maybe about like that. And we're the point, that's a distance of 2 from the origin, when we have an angle of 30 degrees with the positive x-axis. We can convert to rectangular by taking 2 times the cosine of pi over 6 for my x, and 2 times the sine of pi over 6 for my y. And that's the point 2 times square root of 3 over 2, or square root of 3 for x, and 2 times a half, which would just be 1 for y. So the xy coordinates of my point would be the coordinates root 3, comma 1. We can also take rectangular coordinates and convert them into polar coordinates. First off, we use one of two versions for determining r from x and y. And that comes from our original sketch where we have some point. It's got xy coordinate, say xy, gives me a right triangle with hypotenuse r, adjacent side x and opposite side y, and so by the Pythagorean theorem, my hypotenuse is x squared plus y squared, and that tells me how to get the r from the x and the y. I can also take the square roots of both sides, and then I would have r by itself. Now, the theta's got a little bit more to it, because in order to find theta, we use the arctangent function. But the arctangent function only provides angles that are between minus pi over 2 and pi over 2. And sometimes our angle is beyond that range. So whenever we take the arctangent to find theta, we have to remember that we might have the result that arctangent gives, or we might have to add pi to it, or 180 degrees to it, if it turns out the angle of the point we need is in quadrants 2 or 4. If it's been a while since you've seen those quadrants labeled, that's quadrant 1, quadrant 2, which would have angles between pi over 2 and pi. Quadrant 3 goes from pi to 3 pi over 2, and quadrant 4. Now, according to our picture, the tangent of theta would be the opposite side over the adjacent side, and that's why we would think of theta as the inverse or arctangent of y over x. But again, just using arctangent gives us a value that would land in the first or fourth quadrants. So if we know the point is in the second or third quadrant, we have to add pi to it. Here's an example of when we would have to do that. Let's convert the point minus 2, 2 to its polar form. So minus 2, 2, minus 2, minus 2 would put me in the third quadrant. There. Now the radius, or r in this case, would be the square root of minus 2 squared plus minus 2 squared. So that's going to be the square root of 4 plus 4 is 8, or 2 root 2. The theta will be the inverse tangent of minus 2 over minus 2. And here we see why we get a difficulty with inverse tangent, because the minuses cancel, and I get the same result I would get if I just took the inverse tangent of 1, and the inverse tangent of 1 is pi over 4. But pi over 4 would put me here. And I know that the point I'm looking for is in the third quadrant, so I add pi, or 180 degrees, to that pi over 4. And I get my final angle, 5 pi over 4. So that's going to take my theta all the way around to 5 pi over 4, which is what I want. And my polar coordinates would be 2, root 2 5 pi over 4. Now it might have occurred to you looking at some of these drawings that theta actually is not unique. For example, for this last point, we could have taken theta instead of positive 5 pi over 4, we could have taken it to be a negative 3 pi over 4. And that's true of any point in polar coordinates. There's always not just multiple, but an infinite number of ways of representing a point. So we could have written the same point as 2 root 2 minus 3 pi over 4. We could also write it as 2 root 2 and then add 2 pi to 5 pi over 4 and get 13 pi over 4. And that would represent going around the circle more than once before ending up at the angle that we want. In this example, we see how to do a conversion from a polar equation to a rectangular one. We start with the equation r is equal to 2 sine theta. And we want to convert that to x and y, remembering that our relationships are r squared is equal to x squared plus y squared. X is equal to r cosine theta, and y is equal to r sine theta. Now it would be nice on the right hand side if that 2 sine theta had an r in it, because then I could substitute a y in. And the fact that it doesn't have an r in it means I need to arrange for one. So I'm going to multiply on both sides of my equation by r. When I do that, I can now substitute x squared plus y squared on the left, and I can plug in the y for the r sine theta on the right. We could stop here, but I think it is useful to do a little bit more algebra. And what I'm going to do is complete the square after I move that minus 2y over. The x is already a perfect square. I want to write y in terms of a perfect square, so I take 1/2 of the negative 2 and square that, so that would be a minus 1 squared, and I have to add that to both sides of the equation. When I have completed the square, I can now write the left-hand side as x squared plus the quantity y minus 1 squared. We might recognize that the resulting equation is a circle of radius 1 centered at the point 0, 1. So that looks like 0, 1 is here, and we've got a circle of radius 1 there. Our task here is to take a rectangular equation and turn it into one using polar coordinates. Once again, we're going to make use of the relationships we know about. Now we could just take every value that we see, every term that we see that has an x in it, and plug in r cosine theta. And we can take every term that has a y in it and plug in r sine theta. But if we factor on the left-hand side first, then we can save some work, because what we see on the left is is I have 3 times x squared plus y squared. And that allows me to just plug in r squared instead of the more complicated expressions involving r in cosine, r in sine. The rest of the x's and y's I do need to substitute using the r sine theta and r cosine theta relations. I can simplify this a little bit, and once we've done that little bit of simplifying, we'll just leave it here. Next, we take a look at some graphs in polar coordinates. Some common ones that are easy to write down in polar coordinates are circles, or at least some particular circles. Here's the easiest one to do. We can define a circle by the polar equation, say r equals 2. What that tells me is that the r is 2, so I'm a distance of 2 from the origin. The theta doesn't appear in the equation, so the theta can be anything. And so we get a circle of radius 2 centered at the origin. Any equation of the form a cosine theta, that's going to be a circle that has a center on the x-axis and passes through the origin. And an equation like b sine theta, that's going to be a circle with center along the y-axis that also passes through the origin. We can take a look at examples more carefully when we have something to help us with the graphing. The centers of these circles will be at a over 2 for the x value and b over 2 for the y value. Certain kinds of lines are also easy to write down in polar coordinates. The easiest would be lines through the origin, and that's where we just specify what the angle is. If I specify what the angle is, I don't really care so much about r, so that r could be anything. And I would have both positive values of r and negative values of r pointing down and to the left. We can do horizontal lines. So in Cartesian or rectangular coordinates, the equation y equals 2 would be here. And in polar coordinates, we would set the expression for y, r sine theta, equal to 2, so that r would be 2 over sine theta. And as we let theta vary, being careful not to divide by 0, we would trace out a horizontal line at y equals 2. And then similarly, we can do vertical lines. If, for example, we wanted the line y equals 3, then we would set our cosine theta equal to 3, so that r would be 3 over cosine theta. I've included a link in the PowerPoint to a grapher that'll help us visualize some of the more complicated graphs in polar coordinates. This is an applet that allows us to graph 3 polar equations at once. Let's just deal with one at a time. Right, in the last slide, the claim was we can do a straight line by taking 3 divided by cosine. And we see that that's plotted now, and this slider allows us to increase the angle theta and watch how the point is traced out as theta goes from 0 to about 6.28. You might recognize that as 2 pi. So we go from 0 to 2 pi. And see how we trace out the line. What about a circle? So the claim was that if we had something like 3 times the cosine of theta, that's going to be a circle along the x-axis with center at about 1.5. So that's what we have here. And as we trace from theta equals 0 to 2 pi, notice that we go around twice for this one. We can back it up. And we could look at particular points. So where I've stopped here has a theta of about 0.9 radians and a radius of about 1.85 radians. That puts us right at that blue dot. And as I increase it, we continue to just plot the angle followed by the radius. And note that we do have negative values for r. So if my theta is about 2.5, that puts me over here. But then with a minus r, we can still land on the circle. All right, there are many more interesting sorts of graphs. Let's take a look at the default graph 2. Can see that when the equation is 3 sine of 3.5 theta, we trace out sort of petal shapes in the graph. And what about the third graph, 3 cosine 3 theta? It's got a 3-petaled flower. And if we go back and adjust first equation, stop showing the third and show the first, then we get the shape of kind of a lima bean. These are called limacons. Right, so there are lots of different kinds of polar graphs. You can feel free to experiment with these as you wish. I'm not going to ask that you remember the names of all the shapes, some of the common ones, but I did want to make you aware that you can get some fairly interesting shapes. Now, everything we've done in calculus, we can do again with polar coordinates. We can talk about tangent lines, how to find those in polar coordinates. We can do arc length to find the length of a polar curve. And we can do areas that are enclosed by polar curves. We're only going to do areas, and we're only going to do fairly basic examples using in finding areas. In order to make progress finding area in polar coordinates, we need to know or recall how to find the area of a sector of a circle. So the shaded area here is the sector that we say is subtended by the angle theta. And the circle here has radius r. So we define the area of the sector just by what percentage of the total area of the circle it represents. Because the total circle has 2 pi radians in it, the percent or fraction of area represented by this sector would be theta over 2 pi. So the area of the sector would be theta over 2 pi times the area of the circle. Okay, so we have here, that's the fraction of area represented by the sector. And this is the area of a circle, radius r. The pi's cancel, and so in the end we just get this formula for the area of a sector. Whatever the angle theta is, multiply that by 1/2 r squared. A review of our basic method for finding integrals. We split the problem into pieces we know that approximate the situation, like we did for rectangles when finding area in rectangular coordinates. Figure out the area of each piece. Approximate the total area by adding up all the pieces. Get an exact solution by taking a limit as the number of pieces goes to infinity. And finally recognize that what we've done is set up an integral, and then we evaluate it using the fundamental theorem or a computer. The idea is the same in polar coordinates. We split the problem into pieces we know that approximate the situation. In this case, we're going to use sectors of circles. We write down the area of each sector, approximate the polar area by taking the total by adding up all the sectors, get an exact area by taking a limit as the number of sectors goes to infinity, finally recognize the integral and evaluate with the fundamental theorem or a computer. If we start off with a function r equals f of theta, and our picture is going to look something like this. So we've got r equals some function of theta, and we are interested, say, in the area enclosed by the polar graph between 2 angles alpha and beta. So notice this is a little different than the rectangular setting. It's not the area under the curve, it's this area enclosed by the curve given the 2 angles. We begin by drawing a typical piece. So let's call that my r sub I. And the angle for that sector, I can't draw it in the picture, but that's going to be my delta theta I. And I know that the area of this piece is roughly the area as if it were the sector of a circle. So the area of a piece we'll call 1/2 ri squared delta theta I. That's the area of that thin sector that I've drawn. And then we need r in terms of theta. But remember that r is just the function f of theta. So that's what the area of a typical piece of my polar area would look like. I would envision adding up a whole bunch of those, taking a limit, and then finally we would end up with what's going to be our formula for the area enclosed by the polar equation r equals f of theta between alpha and beta. This example asks us to find a polar area. So we need the area enclosed by the graph r equals 3 sine theta, and then we're also asked to check the result with geometry. Now the graph of r equals 3 sine theta represents a circle of radius 1.5, centered at the point 0, 1.5. We can verify that by taking a look at our polar grapher. Where instead of 3 plus 2 cosine theta, I'm going to want 3 times sine theta. Okay, so the blue dotted figure is the outline of our graph. And now we're going to need limits on our integral representing the starting point, which should be theta equals 0, and then the ending point that traces out the graph. And this is an example of where things can get a little tricky in polar coordinates. So as I trace the graph out, notice that I've done the whole thing once I've gone from 0 to pi. If I continue, I get a second tracing of the graph. And if I wasn't careful and took my limits from 0 to 2 pi in the integral, I would end up with double the area I want because I would trace the figure out twice. So what we have to notice here is that the full graph gets traced out from 0, where 3 sine 0 would be 0, to pi, where 3 sine pi would also be 0. So we start at the origin, end up back at the origin, and that all happens between theta equals 0 and theta equals pi. Now to find the area traced out, I use the formula for the area of a polar graph. I'm going 0 to pi, 1/2, 3 sine theta, all squared, d theta. So that's 9/2. 0 to pi, and now I need to integrate sine squared theta d theta. This is one that we've done. It's one of the tricky integration by parts integrals where we have to let u equal sine theta and v prime is sine theta, and then in the middle of it you have to use a trig identity and then collect integrals on one side to get the final result. The resulting antiderivative for sine squared theta is 1/2 theta minus sine theta cosine theta, and I'm evaluating between 0 and pi. That result is going to be 9/4 pi. If I plug in theta equals pi, I get pi over 2 minus, now the sine pi is 0, so that would go away. And if I plug in theta equals 0, I would get 0 minus 0. So the only piece of this that gives me a contribution is when I plug theta equals pi in, and then the 9/2 combines with the pi over 2 to give me my 9/4 pi. To check this result with a result from geometry, we know the area of a circle is pi r squared. The radius of this circle is 1.5, which is the same as 3/2. And so I get 9/4 pi here as well, which checks out. That's going to do it for polar coordinates for us. We'll have some problems to do, and we'll work on those next time.